Welcome to Basics of Vaporizers, Part 2. In the last video, we have learnt the basic properties of gas and vapor and all the factors that affect the conversion of a liquid inhalational anesthetic agent into its vapor for clinical use as an inhalational anesthetic in anesthesia. Now, when we talk about vaporizers, we hear so many terms: concentration calibrated, bubble through, injection type, out of circuit, in circuit, draw over vaporizer, plenum vaporizer, temperature compensated, Tech 2, Tech 3, Tech 4, Tech 5, Tech 6. What do they all mean? It is so very confusing. So now let us go step by step and understand how a vaporizer is constructed, how it works, and what do all these mumbo jumbo of important sounding words actually mean. On October 16, 1846, at the Massachusetts General Hospital in America, William Morton gave the first public demonstration of anesthesia using diethyl ether. He used a device of his own making, consisting of a glass bulb with two orifices and containing sponges soaked in ether. One of the orifices was a mouthpiece through which the patient breathed in ether vapor, while at the same time drawing in air through the other. As the air passed over the sponges, more ether vaporizes, maintaining a steady supply of anesthetic to the patient. Fortunately, the low boiling point of ether means that vapor is produced quickly and at a sufficient concentration to maintain anesthesia. However, this was a very rudimentary device since the vapor output was highly variable. This is an illustration of a chloroform inhaler used in 1850s by the British anesthetist John Snow. The mask was made up of lead and molded to the patient's features. As the patient drew in breath, the air became impregnated with the chloroform in the chamber at the lower right. This is the Schimmelbusch mask, which was designed in 1890 by Carl Schimmelbusch. This hinge-framed mask holds a piece of lint or cloth. Ether or chloroform is dropped onto the material and the mask held onto the patient's face. The anesthetic evaporates and is drawn through the material and inhaled by the patient. The depth of anesthesia could easily be altered by changing the rate at which the liquid anesthetic is dropped onto the mask or lifting the mask from the patient's face. So, vaporizers have evolved from simple inhaler devices to today's modern sophisticated ones, which are flow regulated, temperature compensated, concentration calibrated, direct reading, controlled, and unaffected by positive pressure ventilation. Coming to classification of vaporizers, there are various ways in which vaporizers can be classified. It is important to understand this classification in order to understand the functioning of the vaporizers. So we will see each one of these one by one. First is the classification based on the method of regulating output. Based on this, vaporizers can be classified as variable bypass or measured flow vaporizers. As we have already discussed in our first video, in order to give clinically useful concentrations of the inhaled anesthetic agent, we dilute this with fresh gas. Now this can be achieved in one of the two ways. One, by having an adjustable proportion, that is the splitting ratio, of gas that either enters or bypasses a vaporizing chamber called variable bypass vaporizer, or two, by adding vapor directly to the fresh gas flow, that is measured flow vaporizers. Now coming to variable bypass vaporizers, the vapor pressures of most anesthetic agents at room temperature are much greater than the partial pressure required to produce anesthesia. To produce clinically useful concentrations, a vaporizer dilutes the saturated vapor. Now let us see exactly how a variable bypass vaporizer, which is schematically depicted in this figure, works. To produce clinically useful concentrations, a variable bypass vaporizer dilutes saturated vapor with fresh gas. So how is this achieved? This can be achieved by splitting the gas flow that passes through the vaporizer. Now this is a vaporizer. So we have an inlet, an outlet, and a vaporizing chamber. The liquid anesthetic is in the vaporizing chamber, and it is here that it gets converted into anesthetic vapors. Heat is generally applied to this liquid to maintain the concentration of liquid getting vaporized, as we have already discussed when we discussed the physics. Now fresh gas enters through the inlet. This fresh gas is generally a mixture of oxygen and nitrous oxide or oxygen and air. As we can see in this diagram, there are two ways this gas can proceed. So this way the gas goes to the vaporizing chamber and this way it enters here. This is the bypass. So some fresh gas enters the vaporizing chamber to get saturated with the inhalational anesthetic vapors while some gets bypassed. Now these two gases mix at the outlet so that we get dilution of the gas that is saturated with anesthetic vapors. So basically it is called bypass because some part of the fresh gas flow bypasses the vaporizing chamber and goes directly to the outlet. Now why is it called variable? So how much amount of fresh gas flow is bypassed can be adjusted by controlling this control dial on the vaporizer. The dial will control what ratio of fresh gas flow bypasses the vaporizing chamber to that of the gas that enters the vaporizing chamber. This also makes it concentration calibrated. Both gas flows joined downstream of the vaporizing chamber where gas exits the vaporizer at the desired concentration. The ratio of bypass gas to the gas going to the vaporizing chamber is called the splitting ratio and depends on the ratio of resistances in the two pathways. This is very important because the SVP of most anesthetics is very high as compared to their minimum alveolar concentration needed for anesthesia. Let us take the example of sevoflurane. The saturated vapor pressure of sevoflurane at room temperature, that is 20 degrees Celsius, is 157 millimeter of mercury. Now, fresh gas flow containing 100% oxygen flows over this and gets completely saturated with sevoflurane. So, now it carries 157 millimeter of mercury sevoflurane in it. So, what is the concentration? Now, we know that the concentration of the gas is given by vapor pressure divided by the atmospheric pressure multiplied by 100. If we put in the values, 157 divided by 760 multiplied by 100 is equal to 21%. Now this is 21% of total is too much for clinical practice and it is dangerous. We don't need so much concentration of sevoflurane for our inhalational anesthesia. So we can't allow 100% fresh gas flow to get saturated with sevoflurane. We need to bypass some of it. Now, how much do we bypass so that we get clinically relevant concentration of sevoflurane? Suppose we've split it 50-50. So let us assume half of the gas will get saturated with sevoflurane. So the vapor pressure of sevoflurane will be 78.5 millimeter of mercury, that is half of 157. So resultant concentration will be 78.5 divided by 760 multiplied by 100, that is 11%. But we know that the MAC of SIVO is around 2%. So this concentration is still very high. So we can change the amount of anesthetic delivered to the patient by changing the splitting ratio. Now let us assume we split it 10% and 90% so that only 10% goes to the vaporizing chamber. So the fresh gas flow will have 10% of SVP of sevoflurane, which will be 15.7 millimeter of mercury. So using the same formula, concentration will be 15.7 divided by 760 multiplied by 100, which is 2.1%. This is around 1 MAC for sevoflurane. We can also calculate the splitting ratio of sevoflurane by using mathematical calculations. So now we know that the SVP of sevoflurane at 20 degrees Celsius is 21 kilopascals, that is 157 millimeter of mercury. So sevoflurane concentration is SVP divided by the atmospheric pressure multiplied by 100. So 157 divided by 760 multiplied by 100 is equal to 21%. So splitting ratio can be calculated using the formula splitting ratio is equal to desired concentration divided by the maximum concentration minus the desired concentration. So 2 divided by 21 minus 2 is equal to 2 upon 19, that is 0.11 or 11%. This means that 11% of fresh gas flow will have to pass through the vaporizing chamber to give a concentration of 2% of sevoflurane and 89% of the gas will be bypassed. 89% of the fresh gas flow. A summary of gas flow splitting ratios for different agents is summarized below. The other way of regulating vaporizing output is the measured flow method. In the now obsolete measured flow, non-concentration calibrated vaporizers such as the copper kettle A measured flow of oxygen is set on a separate flow meter to pass to the vaporizer, from which vapor emerges at its saturated vapor pressure. This flow is then diluted by an additional measured flow of gases such as oxygen, nitrous oxide, air, etc. from the main flow meters on the anesthesia machine. With this type of arrangement, calculations are necessary to determine the anesthetic vapor concentration in the emerging gas mixture. Coming back to the classification of vaporizers, let us now see the classification based on the method of vaporization. Based on the method of vaporization, vaporizers are classified as flow over, bubble through, or injection type. Flow over are further classified as with wicks and without wicks. In a flow over vaporizer, a stream of carrier gas passes over the surface of the liquid. As the carrier gas passes over the surface of the liquid anesthetic agent, it picks up the anesthetic molecules, creating a mixture that is delivered to the patient. However, in the basic design, this vaporization is not very efficient. If one uses a high fresh gas flow, the vaporization process can't keep up with so much gas arriving in the vaporizing chamber. The result is that relative to the high flow of fresh gas flow, the amount of anesthetic agent vaporized is inadequate. So this means that at high flows, the basic vaporizer delivers less anesthetic concentration than is set on the dial. The solution to this is increasing the area of the carrier gas liquid interface so that it can enhance the efficiency of vaporization. This can be achieved by employing wicks that have their bases in the liquid. The liquid moves up the wick by capillary action. Most of the vaporizers used in anesthesia today employ this vaporization method. The increased surface area improves the efficiency of vaporization of anesthetic molecules and allows more molecules of the anesthetic to escape into the carrier gas. Another method is to add baffles or spiral tracts to direct the flow of carrier gas. These structures lengthen the duration of gas over the liquid anesthetic, allowing a prolonged interaction of the carrier gas with the liquid anesthetic, in turn resulting in more efficient vaporization of anesthetic molecules and their pickup by carrier gas. Tech vaporizers use wick system for a consistent anesthetic delivery, while Goldman vaporizer has a flow over mechanism without wicks. In bubble through vaporizers, the carrier gas is bubbled through the liquid anesthetic agent. Some of the fresh gas flow is bubbled through a disc made out of a special material, sintered disc, that is very porous. The disc is submerged into the liquid anesthetic agent, and when fresh gas is sent through it, a large number of tiny bubbles form. The tiny bubbles of fresh gas have a very large total surface area and thus become fully saturated with vapor efficiently. Example of bubble through vaporizer is the copper kettle. Coming to injection type vaporizers, certain vaporizers control the vapor concentration by injecting a known amount of liquid anesthetic into a known volume of gas. The fresh gas flow coming from the flow meters does not split into two streams. There is only one stream for the fresh gas flow, and into this stream the liquid anesthetic agent is directly added. This is seen in desflurane Tech6 vaporizer. Coming to the next method of classification, based on the resistance offered, vaporizers can be classified as draw over and plenum vaporizers. In draw over vaporizer, the carrier gas is drawn in by negative pressure through the vaporizer developed by the patient's respiratory efforts, or through a self-inflating bag with a one-way valve placed downstream from the vaporizer, as can be seen in this diagram. So the features of a draw over vaporizer are: the design is simple, it gives low resistance to gas flow, performance is dependent on the minute volume of the patient, it was used with agents like ether and chloroform, the performance was variable and calibration inaccurate, there is no temperature compensation. Examples are Oxford miniature vaporizer and EMO vaporizer. Plenum vaporizers, carrier gas from higher pressure source than the ambient pressure is pushed through the vaporizer to take up the anesthetic vapors. As you may have guessed by now, all variable bypass vaporizers are plenum type. Features of plenum vaporizers: high resistance to gas flow, performance is independent on the minute volume of the patient, variable bypass positioned out of patient's breathing circuit, vaporizer can be accurately calibrated to deliver a precise concentration of inhaled anesthetic vapor over a wide range of fresh gas flows. Example is Tech vaporizer. The plenum vaporizer is driven by positive pressure from the flow meter and is usually mounted on the machine. The next method of classification is based on presence or absence of temperature compensation. The vaporizers are classified as temperature compensated by altered flow, supplied heat, or both, and temperature non-compensated. Now, why do we need temperature compensation? As we have discussed in our first video, as a liquid is vaporized, energy in the form of heat is lost. As the liquid temperature decreases, so does the vapor pressure. In order to maintain a constant vapor output with fluctuations in liquid anesthetic temperature, various methods are employed. Older vaporizers, such as ether vaporizer, come under the vaporizers that are not temperature compensated. So the question is, how can we achieve temperature compensation, and how can we compensate for the fluctuations in vapor output resulting from fluctuations in temperature? The changes occurring in the vapor output resulting from temperature fluctuations can be adjusted by altering the flow of gas passing through the vaporizing chamber to compensate for the changes caused due to the temperature. How is this done? Now this can be done either by using bimetallic strips or ether-filled bellows. Let us first try to understand how bimetallic strip works. When a block of any material is heated up, it tends to expand. Different materials expand by different amounts based on a property called their coefficient of thermal expansion. Now imagine that you take two blocks of two different metals and bind them together and then heat them up. What will happen? The material with the larger coefficient of thermal expansion will try to get longer than the other material. Now since the two are bonded together, the only way this can happen is by bending. This is exactly how a bimetallic strip works. This is an incredibly simple but useful device that can be used to convert a change in temperature into mechanical displacement. Thus, the bimetallic strip consists of two metals having different coefficients of thermal expansion that expand and contract at different extents when heat is applied or lowered. These differing expansion rates of the two metals cause the strip to bend in either direction with changes in temperature. This bending movement of the strip is used to adjust the position of a needle valve, which controls the flow of fresh gas into the vaporizing chamber versus the bypass channel. When ambient temperature increases, the strip bends in a way to increase the flow through the bypass channel and reduces the flow in the vaporizing chamber. This automatically decreases the amount of gas that picks up the anesthetic vapors. When ambient temperature decreases, the strip bends in the opposite direction, decreasing the flow through the bypass channel, increasing the flow in the vaporizing chamber, thus compensating for the reduced vapor pressure by allowing more gas to pick up the anesthetic vapors. Bimetallic strips are specifically used in variable bypass vaporizers. Some vaporizers use the property of expansion and contraction of bellows filled with a liquid. Ether-filled bellows work on the principle of thermal expansion of ether. Ether has a high coefficient of thermal expansion. As the temperature rises, the bellows expand. This mechanically alters the flow of fresh gas flow and diverts more gas into the bypass channel. Thus, vapor uptake by the carrier gas is reduced, and reverse happens with lower temperature. The bellows contracts and allows more gas to flow into the vaporizing chamber, thus increasing the uptake of anesthetic vapor to compensate for the reduced vapor pressure. Another method of thermal compensation is by directly supplying heat to the vaporizer. The Omeda Tech 6 vaporizer is specifically designed for desflurane. Desflurane has a high vapor pressure and is highly sensitive to temperature fluctuations. The boiling point of desflurane is 22.8 degrees Celsius, so it will boil at room temperature. This will result in cooling of desflurane due to the latent heat of vaporization, resulting in inconsistent vapor pressure and hence inaccurate vapor output. In Tech 6 vaporizer, there is an electric heater that maintains the temperature of desflurane constant at 39 degrees Celsius. Maintaining the temperature of desflurane at 39 degrees Celsius ensures that it stays in a stable vapor form and makes the vapor output consistent and accurate. An internal thermostat monitors and regulates the temperature. Any drop in temperature activates the heater so that the temperature is maintained stable at 39 degrees Celsius. This is a diagrammatic representation of the same. But right now we will not go into the details. I will discuss desflurane vaporizer separately in a dedicated video. Coming to the classification based on agent specificity, vaporizers can be multi-agent or agent-specific. Older vaporizers like Goldman vaporizer were multi-agent. Modern vaporizers like Tech vaporizers are agent-specific. They are individually customized according to the chemical properties of a particular agent, such as the saturated vapor pressure, the boiling point, and the minimum alveolar concentration of that agent. Agent-specific vaporizers cannot be used interchangeably. Coming to the classification based on location, vaporizers can be classified as in-circuit and out-of-circuit. There are two possible locations for a vaporizer within an anesthesia breathing circuit. If it is integrated directly into the breathing system, it is called vaporizer inside circuit, while when the vaporizer is located outside the breathing system, it is called vaporizer out of circuit. Goldman vaporizer is an example of vaporizer in circuit, while Tech vaporizers are vaporizers located out of circuit. With vaporizer inside circuit, the vaporization takes place directly within the gas flow that goes to the patient. The vaporizer is placed downstream to the fresh gas flow. The vaporizer output depends on the patient's efforts or the pressure generated by the mechanical ventilator. So the output is extremely variable and depends on patient's ventilatory parameters like respiratory rate and tidal volume. Precision in accurate delivery is also lacking. As the vaporizer is located in the breathing circuit, it increases the resistance to breathing. In vaporizers out of circuit, the anesthetic vapor is mixed with the carrier gas before it can enter the breathing circuit. This setup is common on the modern anesthesia machine. Vaporizer is located upstream of the breathing circuit. The output is not dependent on patient's respiratory parameters and hence is accurate and precise. As it is located out of circuit, it does not create resistance in breathing system. I hope I have given you a concise and comprehensive understanding into the classification of vaporizers. In the next video, I will discuss the operating principles of variable bypass vaporizers, the effects of intermittent back pressure such as pumping effect and pressurizing effect, and we will quickly run through all types of various vaporizers and see, with all the knowledge that we have gained till now, whether we can correctly classify them and understand their working. Before ending, I would like to mention this simple yet very useful website, How Equipment Works, by Dr. Prasanna Tilakratna. The illustrations created by him make understanding the working of every equipment very easy. I have used some of his illustrations in this video as well as the next one. His content is free to access on his website and I recommend all students to visit it at least once. Thank you.